I want to start just by welcoming everyone to our October webinar. Thank you so much for joining us. My name is Matt Del Bono, and I'm an Extension Support Specialist here at the Glaze Consortium. And today we have a presentation from Dr. Kale Harbick from the USDA on Virtual Grower, a program which can quantify energy consumption associated with greenhouse production. And so before we get started, I want to welcome you all here today with just a few minutes of information about our organization, Glaze, and then we will jump into our presentation. So Glaze is the Greenhouse Lighting and Systems Engineering Consortium, and we are out of Cornell University. And we're here to transform greenhouse lighting and systems management to support climate smart CEA. We do so by conducting research and educating growers so that emerging technologies can be hopefully adopted faster and help growers save money and reduce the environmental impact of energy use in greenhouses. So these are the three main ways in which we serve our members. As I mentioned, our research is very focused on greenhouses, but also indoor agriculture, and we seek to help facilitate technology transfer by showcasing the results of technology's impacts on plants. We also provide webinars, our annual short course, and other workforce development opportunities and educational programs for growers. And finally, our membership values the networking benefits that come with participating in the Glaze Consortium, both at our meetings and our annual summit. So our members are very valued, and we hope that you are interested in potentially joining Glaze. For those of you that would like to learn more, please feel free to contact our team or myself directly to learn more about our membership categories and the benefits that comes with Glaze membership. I want to take a moment and share a new Glaze initiative this year called Vivid Canopy, where folks working in the CEA industry can connect with organizations and showcase how they are leading by example and hiring a more diverse workforce. And actually, next month, we're hosting a Vivid Canopy reception on November 6th at the 2024 Glaze Summit in Montreal. Speaking of the summit, we encourage you to register for our event in Montreal on November 6th. Our theme this year is dynamic lighting, and we have a very exciting agenda published on our website. The event will feature a keynote presentation from Tessa Pocock. We have a US and Canadian grower panel, 2 separate research panels, and other presentations on new technologies. So we encourage you to register today as spots are limited, and we hope to see you there. Finally, a special thank you to our anchor partner, Saloom Technologies, as well as Hogendorn Growth Management for sponsoring the networking event. So today, as I mentioned, we are learning about the Virtual Grower Program, and I have the pleasure of introducing our speaker, Dr. Kale Harbick, who is a research agricultural engineer at the USDA. Dr. Harbick studied computer science and robotics at the University of Southern California, earning a PhD in 2008. He's researched crater detection for Mars landers and autonomous helicopters for NASA before shifting his career focus to energy. Dr. Harbick managed a program at the Oregon Department of Energy, which implemented energy efficiency measures in over 800 K-12 schools. And he also serves as an advisory board member of local stakeholder groups, such as the Agricultural Incubator Foundation. His research now focuses on environmental controls and modeling of energy and light. So, Dr. Harbick, I know you have a lot to cover, so I will invite you to say hello to our audience and take it from here.
Thanks, Matt. I'll go ahead and try and share.
Sure. And while Dr. Harbick's pulling up his presentation, I'll also just note to our audience that we do have time for questions at the end of this presentation. So we really encourage you to submit them via the Zoom Q&A as we go. That way we've got some to jump right into when Dr. Harbick finishes his talk. So thank you so much.
Okay, thanks for joining, everyone. So I wanted to give some information today about Virtual Grower and some of the new updates we've got coming soon, and also just a general overview of what is energy modeling, why do we do it. So let's see. There we go. So energy modeling, we're talking about buildings specifically. So what we're trying to do is quantify how much energy is used by the building each year. So one of the metrics we use for that is called EUI, Energy Use Index. And that is basically the energy consumption divided by the area of the building, footprint of the building. So obviously, it's very dependent on several factors, such as what are the conditions that you're trying to meet in the building in terms of temperature and humidity. It is very dependent on the location of the building. So we look at things in terms of weather. So the term we use is typical meteorological year, or TMY. So it's not exactly the same as an average set of conditions, but it sort of looks at a period of record that might be 30 years or 60 years for that location, and it tries to construct a typical set of weather conditions for that year. So of course we meet heating and cooling loads with HVAC systems. That's one of the drivers of energy use. And in terms of the models, we size the HVAC according to design conditions. So what that means, it can vary, but basically you look at sort of the worst case weather situation and you take some percentage of that. So maybe 95% or 97%. And it basically means your HVAC system is sized to meet the loads, 97% of the time. And they do that because, if you size the HVAC to meet the absolute worst case, that might be a very expensive system that you're not going to need that capacity most of the time. So when we do these models, I'll talk about the methodologies, but ideally we want to validate the results with measurements of real world buildings. So that might be an energy audit of a building. It might involve looking at utility data. So that data is critical for the feedback loop to improve the software so that we get good, consistent results. One way we use to look at this is in terms of end use splits. So this refers to where is the energy going in the building. So of course we have our HVAC, heating, ventilation, air conditioning. A lot of times we'll include refrigeration for facilities that have a sizable refrigeration load. And we'll look at internal loads such as lighting and equipment. So loads just refers to something that the system has to respond to. So in terms of HVAC, we're looking at either sensible loads or latent loads. Sensible just means the load dealing with the temperature, whereas latent loads deal with humidity, and they're related, but the system needs to address both in order to have proper comfort or proper conditions. And then we can classify loads in terms of external or internal. So external loads include things like thermal conduction through the building envelope. So the envelope includes things like walls and windows. We have ventilation, which is the intentional exchange of outside air with the building air. Infiltration is the unintentional exchange. So they both contribute. Solar heat gain involves direct radiation heat transfer from the sun. And then we have internal loads. So some examples of those, lighting and equipment, we already talked about. Those are electricity loads, but also people. So people give off body heat, people give off moisture through respiration. All of those have to be taken into account when we model the building. So we use various types of technologies and software to do these models. So in the simplest case, we can construct calculations using a spreadsheet, which is very useful in certain situations. And we would classify that as more of a steady state model. And I'll talk more about steady state versus dynamic in a second. So on the residential side, there are many programs that do this. One is called Ecotrope. There's various certifications that software for residential energy modeling can acquire. And this is one of those that is resident certified. Um, in the commercial world, this is where a lot of interest lies in the commercial sector because most of the energy goes to the commercial sector. So this includes things like hospitals, schools, convenience stores, fast food restaurants. All those types of things are in the commercial category. So the gold standard for that is a software package called Energy Plus. So Energy Plus is the engine, simulation engine, and then Open Studio is one of the more common graphical user interface programs that sits on top, so that you can interact with the engine. So this software is very powerful. It's very complex. If you're a software person, it has over 1 million lines of code, so it's very complicated program. People have been working on this for decades. It implements the ASHRAE heat balance method. So that's basically a set of calculations put out by ASHRAE that is a dynamic model for heat transfer and energy flows in a building. And ASHRAE stands for American Society of Heating, Refrigeration, and Air Conditioning Engineers. So they're kind of the standards organization for this. So Energy Plus, a lot of the reason for its complexity is it has to implement all these different HVAC models for all the different types of equipment that you would find in a commercial building. So there are, dozens of different types of systems. It's very well validated for commercial buildings. So there are, special test buildings that have been set up and instrumented to precisely record energy data, and also energy audits of normal buildings have been used to validate these results. For our purposes, one of the issues is Energy Plus, although very good at the commercial building world, is not really suitable out of the box for CEA. So when we look at these different categories, different sectors, we have residential, commercial, and industrial. So industrial is what I would classify as things like, factories. If you have like an aluminum plant, that's a very specialized set of energy processes that's very energy intense, and you need to handle those models with special care. And I would categorize CEA as more on the industrial end of things, because you have a lot of special situations in CEA. You have specialized lighting control systems, maybe specialized HVAC systems. You might have CO2 supplementation, which affects things. You have plants, which are a major contributor to latent loads in the space. So CEA is more complex than most of the programs out there are designed to handle. So let's look at some features of a basic greenhouse energy model. So we have all these different energy flows in the building and coming in and out of the building. So I mentioned before, we have conduction through glazing. So let's say it's the glass greenhouse. We have solar radiation providing heat. We have ventilation and infiltration, exchange of air. There might be some evaporative cooling systems associated with that ventilation, so we can cool the space through evaporative cooling and then exhaust through the fans. We have some internal loads, primarily that is lights, supplemental lighting, and evapotranspiration from plants, which is a sizable amount of latent load, much higher than what people produce in commercial buildings. As I said, we have specialized control systems to deal with greenhouse energy that might involve, different styles of lighting control. You might have timers or threshold control or DLI control. All those will have a different effect on the modeling. Now, in most cases, the model makes a pretty significant simplification, which is what we call a single thermal zone. That means all the area you see in blue is one set of conditions in terms of the model, one set of temperature, humidity, and CO2 conditions. So we'll come back to that assumption later and see how that might affect things. Okay, so once we have that basic set of criteria for the model, we can approach it in two main ways. We have a steady state version and a dynamic version. So the steady state model is more like a set of spreadsheet calculations where you assume that your conditions are being met all the time. That means you have perfect control of your temperature set points and other set points. So in order to do that, you have to assume your HVAC has infinite capacity. It can handle whatever conditions you throw at it. So you set those conditions, you calculate what the HVAC system must do to meet those conditions. And then you usually look at a fairly coarse set of time steps, so it might be hourly data. But the advantage of this method is it's pretty fast. So then the dynamic version, it's using the same underlying physics, but it's using uh, differential equations and solving them in those methods rather than simple spreadsheet calculations. So you're going to simulate both the zone itself, the thermal zone, and the HVAC system. So you will be able to size the HVAC according to some criteria. You'll be able to see, are there conditions where the load is not being met? In other words, if you have a really hot day and maybe your HVAC system is not capable of meeting the set points during that period of time, this type of model will tell you that. You can account for capacitive effects such as thermal mass of air, water, concrete, and other materials, which adds sort of time delay effects to the system, to the model that won't show up in a steady state model. It allows you to do finer time steps and adaptive time steps. So you can subdivide your time steps to get more accuracy or increase them to get more performance, and that's a dynamic process. The disadvantage, of course, is that it's a slower method of calculation, but in general, you'll get more accuracy. Now, there are some cases where it doesn't matter which of these you choose, you'll get similar results. But there are some cases where you would get different results. So we'll talk about that in a bit. So just to scare you a little bit with the math, we're not going to go through this, but this is one example of the type of equation you have to solve in a dynamic heat balance. You're solving that zone temperature equation on the top. The bottom piece is, this is one of the rare differential equations that does have an analytical solution, and that's shown below. So the dynamic model is solving these types of equations for each time step. Okay, so where does Virtual Grower come in? So Virtual Grower initially came out, maybe 15 years ago, and it was designed to do a couple things. We wanted to have a basic energy model for greenhouses and also to be used as a planning tool for growers to look at things like when are harvests due, and there's some floriculture things in there in terms of growth models. So the most recent version on the Windows platform was version 3, which came out maybe 10 years ago. And that was written in Java. It was a downloadable application for older Windows operating systems. So it's difficult to get running on today's systems. It's a steady state model. Again, it uses the single thermal zone assumption, and at that time, it only incorporated high pressure sodium lighting. So when I joined ARS, we wanted to update the software and also make it more accessible. So we moved to a browser version, which means you can use any computer to access it with a web browser. You don't have to download anything. It runs on your local machine. It's written in JavaScript, and we're in the process of converting all the models under the hood to dynamic rather than steady state calculations. The beta that's on the website vgrower.net is still using the single thermal zone assumption, but I'll talk about how we're going to address that in the future. So we made various improvements to it, such as LED lighting and a few other things. So looking ahead, some of the changes we're working on are we're planning to decouple the user interface from the engine. So right now it's all one program that runs on the web, but what we're planning to do is have a separate simulation engine called VGSim, which will run underneath Virtual Grower. So the user interface to Virtual Grower will still be the same as you're familiar with, but it's another way to use the program. So it's really meant for folks like researchers. So folks that have programming experience can use the simulation engine, and they can either write their own interface on top, or they can use it in a set of simulations. And I'll talk about some use cases for that in a bit. But it allows us to do either online or offline processing. Again, it'll have dynamic models written in the Python language, which is one of the most popular programming languages. And it'll have multiple thermal zone options. So what are some use cases for this once we do this? So Virtual Grower, again, is the GUI part. That's how most users will interface with the program. It'll be running VGSim underneath, but you won't have to interface directly with the simulation engine. You'll just use Virtual Grower. So it's maintaining that same user-friendly interface. And it's really meant for things like if I'm a grower and I have one greenhouse operation, I want to simulate it, that's a good tool to use. Or if I have a handful of climates that I want to look at, I can do that. But if I'm maybe a research user and I want to look at every climate, then Virtual Grower is not really the best tool for that anymore, because it'd be very tedious to go through and select all 1,000 different climates in the US and simulate them and then record the data. So it's meant for doing these big batch processing runs of either many different climates, maybe many different parameters in terms of, maybe I want to vary my lighting efficacy over a certain number of values. What does that look like? I can do that sort of parametric analysis. I can do sensitivity analysis. So I can vary certain parameters and see how sensitive the results are to those parameters. I can also, once I have the library, I can run it on high performance computing platforms. So within USDA, we have a platform called SciNet, which we use internally, which we could use for this. And then other folks, a lot of universities have HPC centers that can run software like this, which greatly speeds up the processing. So let's go through an example of how we might use VGSim as a researcher. So let's say I'm studying greenhouses and I want to look at a typical situation, but I want to look at every climate. So in the US. So I'm looking at EUI, again, that's energy use index, or energy per area per year. Let's say I have a glass greenhouse that's 1 hectare, 17 moles per square meter per day is my DLI target. Let's say I have fairly inefficient lighting, maybe that's good HPS or bad LEDs. So around 2 micromoles, 85% natural gas heating. For this, I'm going to assume I have day-wise optimal lighting, which means I'm looking at the natural light I get for each day and then supplementing exactly how much I need to get to 17. Single thermal zone assumption, again, for now, let's say there's no energy curtain. We're going to look at all climates in the contiguous US. And then we want to estimate heating, lighting, and total energy. So this is a plot of all the different weather stations we have for this TMY3 data set. This is the lower 48. So there's about 1,000 stations if you include Alaska and Hawaii, but in the lower 48, there's 900 something. So again, this would be very tedious to create a model for using just Virtual Grower by itself, because you'd have to manually click and select each climate zone. So using VGSim, we can do the same process on a computer and just let it run for several hours. So the runs I'm going to show you took about 6 hours to generate. So first we have heating. So the scale is shown in gigajoules per square meter, and the values that are in between the stations, the weather stations, are interpolated with inverse distance weighting. So you can see, obviously in the northern latitudes, we're going to use more heating energy than in the southern latitudes. Here's a similar picture with lighting. In this case, we're using kilowatt hours per square meter. And again, that is with, fairly crappy lights and a 17 mole target. So obviously in the Southwest and in Florida, we have high natural DLI, so you don't need a lot of supplemental lighting. Now, if we combine those into a total, so we're converting everything to gigajoules per square meter here for our EUI measurement, we get values basically from 2 to 14. And now I'm going to show you all three maps together for comparison. And for comparison, we're also looking at, in the upper left, we have the IECC climate zone map. So this is a different set of climate zones than, like, you might be familiar with USDA plant hardiness zones. That's a different thing. So this set of zones is meant for energy modeling. So it tells you things like, temperature areas and, humidity levels in this map. So you can see, if you compare that graph with the heating plot, there's a high degree of correlation there between the zones you see and the heating requirements. With lighting, it's not as correlated because you have a high dependence on latitude for lighting. Okay, so this is a set of data, but how do we know if it's any good? We want to ideally compare with real world buildings, but the problem is, in most cases, it's pretty difficult to get actual utility data from growers, and there's various reasons for that. But some progress was made on this front last year by Resource Innovation Institute. So they produced this report, which has, I pulled out one of the graphs on the right, but this is basically a set of 12 growers that participated and supplied energy data and yield data, and it was anonymized and aggregated to produce various benchmarks in this report. So, this is the first report of this type that I've ever seen, and hopefully there'll be more like this to come. But it requires, it really benefits from more participation. So you can see there's only 12 in this case, but the good news is that when we look at energy per weight of sellable products, so, well, EUI is great, but it doesn't really tell us anything about what we're producing, right? So it doesn't tell us about the yield of the crops that we're producing. If I have no supplemental light in a greenhouse, I'm not going to use any lighting electricity, but I'm not going to produce as much as someone who does use supplemental light. So a good metric for this is looking at energy per weight. So for this, we're assuming 120 kilograms per square meter per year in terms of something like head lettuce production. And that number comes from Finger Lakes Fresh values. So if we convert the results from the previous slides into this metric, energy per weight of sellable product, we end up with, in English units, we end up with about 50 kBTUs per pound on the top end. So depending on the climate, it'll be lower than that. So those results agree very closely with the two left columns in the chart. The three columns on the right are more like vertical farming type applications, which use considerably more energy per pound of sellable product. So in terms of greenhouse results, we're seeing strong agreement with the limited amount of real world data that we have access to. Okay, let's come back to this thermal zone assumption. So as I said before, a single thermal zone assumption means you have a homogeneous climate where you have a single temperature, humidity, CO2 set of conditions in the greenhouse. But of course, we know in reality that's not really the case. So, it might look more like the picture on the right to a first approximation, where you have these layers of temperature profiles. You might have hotter air at the top because the sun is heating the top surface of the glazing and hot air rises. So that layer at the top by the ridge will typically be warmer than lower layers. In the middle, you see that that blue stripe, that refers to the canopy microclimate. So you might have extra humid air near the canopy because of ET. It might be more humid than other parts of the greenhouse. It'll also typically be cooler in temperature than other parts of the greenhouse because that evapotranspiration also causes a sensible cooling effect with the canopy. So what are the implications of simulating these layers is you can simulate heat transfer between each layer. So you're not just having one set of conditions now. It's sort of like you have 5 rooms that are all connected together and you're simulating the conditions that interact between them. So that's one of the options that we're incorporating into the next release of Virtual Grower. It remains to be seen what conditions, what are the impacts of this in terms of when can I get away with the single thermal zone assumption in terms of how much accuracy am I sacrificing? We don't really know a good quantitative answer to that yet. I suspect that this will matter more in warmer seasons because you'll have a greater stratification effect. But that's just a hypothesis right now. So something else we can do is incorporate a technology called computational fluid dynamics, CFD. So that's where we take it a step further. We don't just have a set of layers of thermal zones, but we actually simulate cells of air. And basically there's a grid on the picture on the right, and you have a condition at each point in the grid. This is about 1,000 cells, I believe. So you have interaction between a cell and all its neighbors, and then you sort of simulate them all together. So it's kind of like you're simulating a building with 1,000 tiny little rooms. And this presents some interesting pictures because you get to see this, highly distinct canopy microclimate, which is the blue area. You will see this warmer area right above the submental ice, which is in red. So again, that's caused by warm air rising, solar heat gain, the lice themselves. Then you have this flow of air from left to right because you have air coming in on the left from evaporative pads and air going out on the right through exhaust. So all of those flows are simulated, all those convections are simulated in this model. So this was produced with VGSim using a CFD version. So we do plan to release that at some point as well. It needs some work to make it produce good results under a variety of conditions, but these are some preliminary results. And again, it needs some analysis in terms of how much does this affect the end result versus the CFD model versus the layered thermal zones versus a single thermal zone. So we want to do some studies and see under what conditions is it worth going through those that extra computational power that's required to do CFD. So, CFD is very nice because you can simulate all these effects: canopy, microclimate, energy curtains, convection, evapotranspiration, much more accurately than you can with the single thermal zone or layered thermal zone options. But it's a huge computational complexity. It takes way more time to produce these types of models. So, the advantage of HPC, high performance computing, really comes into play. And we certainly plan to leverage SciNet and other resources as we pursue that research. But again, we want to quantify the trade-off. When is it worth going for the full CFD approach, and when is it okay to just use a simpler model? That's one of the questions we're trying to answer. So I want to acknowledge the team members that have worked on Virtual Grower over the past year or so. And of course, there's been many others before that, but these are the most recent folks. And of course, we've had a lot of beta testers giving us feedback, which I greatly appreciate. That's how we discover bugs and make improvements. So everyone is welcome to check it out at vgrower.net and send me feedback. And just a quick plug as well, we're hiring a new scientist in our unit, a research horticulturist, and that's going to be based in Worcester, I believe, Worcester, Ohio, and it closes on November 8th, and the link is there. So I'm happy to take your questions.
Thanks so much, Kale. So we do have some questions here queued up. And the first one I'll actually start with. You probably don't see the log. It was just emailed to me. And then we'll jump into what's been submitted in Zoom.
Sure.
Someone asked, how do you account for the percentage of heat gain from LED or high pressure sodium lighting? Meaning how much percentage LED contributes towards light energy and how much radiative and convective heat gain into the greenhouse?
Yeah, so a lot of this is captured simply with the efficacy number, that micromoles per joule, but essentially the assumption we usually make is that all of the energy produced by the light that is actual light hitting the plant, we're assuming that stays in the greenhouse. Now, in truth, some of it escapes as light pollution, right? But that's a relatively small fraction. Almost all of it stays in the greenhouse as, it ultimately becomes infrared and affects the temperature. So whether the heat is produced as light and then it becomes infrared, or whether the heat is direct sensible just from the heat of the electronics, both of those are incorporated in the model and assumed to have a sensible load on the system. So that, just by the nature of HPS having a lower efficacy, given the same input power, you will have more sensible heat produced from HPS. Now, one of the things that's not being perfectly modeled yet is the direct infrared component. So HPS has a decent amount of direct infrared radiation, and we still need to improve how we're modeling that component.
Very good. So the first question in the Zoom Q&A is from an individual who works as a building energy modeler, and their question is, can you co-simulate VGSim with Energy Plus?
Can you clarify what you mean by co-simulate?
I'll invite the person who submitted this question to maybe follow up with just a bit more information, sure. and we'll move on to the next. So okay. If you could just recomment your question with a bit more info, we'll be happy to take that. So the next question in the chat here is there cooling energy use intensity or only heating and lighting?
So in general, you absolutely want to include cooling. And that's especially true for vertical farms because a sizable amount of energy goes to cooling. I ignored it in this case for the greenhouse model because evaporative cooling is incredibly energy efficient, and it's basically a negligible amount of energy compared to what you put into heating and lighting. So yes, you want to include it, but it wouldn't change the results in this situation very much.
Okay, thank you. The next question is VGSim able to be verified, tested, certified to the American Society of Heating, Refrigerating, and Air Conditioning Engineers standards? Does that functionality exist?
So we are working on, as we incorporate ASHRAE heat balance calculations into VGSim, um, we also want to look at things like, 90.1 standards on like COP, like coefficient of performance for chilling systems, which is again very important for vertical farms. So, that is on the roadmap, but it probably won't be in the very next release, probably in a future release.
Mhm. Very good. The next question is, would a three thermal zone model be sufficient? Greenhouse, sunlit leaf surface, and then shaded leaf surface.
It could be, it remains to be seen. I just showed five there as an illustration, but we need to do some studies to see like what is the optimal number of thermal zones. If you're going to use layered thermal zones, what is the optimal number to simulate under various conditions that gives you the closest, you know, accurate results? And of course, to know that, ideally we'd have the CFD model as well, because that's sort of the most work we can put into it. So we'd want to compare that result with the different layered approaches and see like what is a good number. And that'll allow us to come up with some guidelines to give the users, like, try setting 3 layers or try setting 5 layers, and you should get pretty good results. So I don't know the answer to that yet, but that's one of the things we want to find out.
Let's see. The next question is, can you explain where this is different compared to Caspro?
So Caspro, I have not had any experience with. So it's
Okay.
a good question, but I don't know.
Okay. Thank you. We'll put that one away for now. Um, is there a tool to quantify or size AC unit for a small size 40 by 12 greenhouse?
40 by 12 is usually below the minimum threshold that we study, simply because it's kind of a niche case where, we usually look at, say, quarter acre or above, because the smaller you get, you start to see a lot of strange effects. Like you have a lot of inefficiencies with smaller and smaller equipment. So the bigger the system, the more efficient it is. But also just, commercial scale systems is what we primarily focus on. So, but I would say, AC, we usually, when we say AC, we're talking about mechanical cooling. So that's more the type of system you would see in a vertical farm. Whereas in a greenhouse, you'd more often see like evaporative cooling systems. And, you know, there are some standards put out by ASABE that deal with this. I think one of them is called EP 406, maybe. I might have that number wrong, but it'll tell you basically, like, if I have this square footage of greenhouse, how much evaporative pad area should I have? And there are some guidelines published by ASABE that specifies those sorts of things.
Okay. Thank you. Someone asks, do you have an ETA for the release of the new version of Virtual Grower using VGSim? Will this version be able to model single bay and multiple bay greenhouses as well? Also, how much flexibility in terms of geometry does Virtual Grower offer?
Yeah, so my goal is to get the first version of VGSim out by the end of the calendar year. We have some some plans to do that. And then yes, we can do single bay and multiple bay. I think Virtual Grower can already do that. What you do is usually specify things like the overall dimensions and then the roof shape. So it's mostly looking at things like Venlo style or similar styles where you have, a rectangular structure with either a peaked roof or a curved roof, and there's different shapes that you can select for that roof geometry. So that's the typical geometry selection we have now. But if there's a geometry that you have that's not covered, let us know and we'll see if we can add it as well.
Excellent. The next question is, someone tried looking for a list of the TMY3 sites to determine the one closest to them, but couldn't locate one. Do you have any suggestions for this person?
Okay, so two things I would say here. I believe if you go into vgrower.net and search for your location, it'll suggest a closest TMY3 file for you. But I should say, technically speaking, NREL has deprecated the use of TMY3 in favor of some other file formats. We still support TMY3 because there's so much literature out there that uses TMY3, and we want to have that basis of comparison as an option. But we also plan to implement more recently produced weather data sets, produced by NREL and other organizations.
Very good. So this is our last question here in the chat. So folks, if you have additional questions, please submit them. But we'll circle back to the earlier question about from the building energy modeler asking, can you co-simulate VGSim with Energy Plus? And the follow-up is by co-simulation. We mean use Energy Plus to model the mechanical systems, which it does well, but use VGSim to handle much of the internal loads in biology.
It's a good question. So, in the past, maybe 10 years ago, when I was first working in this area, I took the source code for Energy Plus and added some modules that dealt with internal loads of CEA, like lighting, specialized lighting control systems and ET and things like that. And that was that, we produced good results with that work, but it's not something that I wanted to continue because Energy Plus is such a monster piece of code and, very difficult to add capabilities to. So, when I started at USDA and we had Virtual Grower, I decided that was a better direction to move in. Now, in principle, you can certainly co-simulate if you can feed information between the simulation engines. So, Energy Plus has a way to do that, which I think is not very user friendly. But you could create a sort of glue layer between our API and their API that would allow that co-simulation. And that's how I would do it because, there are some cases where you'd have a constant load that you could just put into Energy Plus, but, these CEA loads are time varying. So it'd be difficult to do that. So I don't know if we're ever going to directly support Energy Plus API connectivity, but it's something we can look at.
Very good. We have a couple more now.
Sure.
Will you be adding corrugated metal or IMP walls to the greenhouse model?
Yeah, we're definitely open to adding material components or, ideally what I would like to do is have full building component library implemented as Energy Plus does. But in the meantime, we'll add some commonly used materials and, definitely send me suggestions for what materials you'd like to have implemented. It's just a matter of, putting in the U values and other parameters for each material, and then you can simulate it just just as easily as the other ones.
Very
And
good.
I should point out too, you already have the ability to do custom uh, key values and material properties, if I remember correctly.
Yeah. So the last question we have here now is, will you get to the point to simulate leaf temperature for different covers, energy curtains and or glazing types above canopy, changing radiation thermal exchanges?
Yes, that's definitely something we would like to do. My colleague Jennifer does quite a bit of work dealing with leaf temperature and cold stress and things like that. And I think it's definitely a capability we would like to have. It's not going to be in the next version, um, but hopefully not too far in the future.
Another question here, since we have time, just came in. When working with shipping containers, do you think the amount of ventilation cost savings would be worth the limited space?
So typically with shipping containers, you know I guess technically you could do a mechanical cooling system or a ventilating evaporative cooling system. Um, I don't have a lot of experience with this type of system. We have a sister lab in South Carolina who has a bunch of shipping containers, and we've talked about instrumenting them so that we can create more accurate energy models of that type of system. But my guess is because of the small area, you know, it's you usually lose efficiency by going small in terms of HVAC. You gain efficiency by going large. So I suspect you're not going to gain much by going to a shipping container footprint.
Very good. Well, folks, we have cleared our question list, so I think I will wind things down here. First, I want to thank you again, Dr. Harbick, for joining us today and sharing this presentation with our audience. And we appreciate the great questions. Thank you to our audience for tuning in. Sorry, we've got one more that I'm going to sneak in, and then we'll break. Will it be possible to manually input ET rates for different crop types?
Yeah. So what I'm envisioning currently is, at least at the most basic level, have an ET rate for lights on and lights off. Of course, lights off, you're typically respirating, but basically have a number that's used when either natural light or supplemental light is present, and that's the ET input. Now, there are lots of more sophisticated ET models we would like to incorporate, Penman-Monteith variations and so forth. So that's on our longer term to-do list. But yeah, it's a very, very important input to the system. It's a huge amount of latent load that the system has to deal with. So we care a great deal about having more accurate ET models.
Very good. Okay, so with that being said, I think we'll wrap things up here. Thank you again, Dr. Harbick, for joining. There's clearly a lot of interest from our audience, and we appreciate the great questions. I will note that this webinar was recorded, and we'll be posting it to our YouTube channel shortly, so you can go back and watch it again or share at your leisure. And thank you to the attendees for joining today. We appreciate you tuning in and learning about Virtual Grower as well as the Glaze Consortium. And once again, we hope you consider attending our annual summit next month on November 6th in Montreal. So please feel free to reach out if you have any questions, and I hope everyone has a great rest of their day. Thank you.
Thanks, folks.